Welcome to the second of two videos on systems of linear equations in Foundations of Mathematics and Pre-Calculus 10. In the first video, we learned that solving a system of equations involves considering two different equations simultaneously. We focus on what it means to solve systems graphically. The focus of this second video will be on solving systems using algebraic methods. Systems of linear equations can be used to model contextualized scenarios in which the values or quantities of two types of items, like adult and child tickets or t-shirts and hoodies, is unknown. Systems can also be used to create an ideal or desired mixture. We'll explore and apply two algebraic methods for solving systems of linear equations. Let's begin with an informal investigation of one of those methods. Consider the following scales. On the scale on the left, one pyramid and two cylinders balances 10 cubes. On the scale on the right, one cylinder balances one pyramid and two cubes. Three cylinders are placed on one side of the scale at the bottom. How many cubes does it take to balance these three cylinders? There are many ways to solve this challenging puzzle. Let's look at just one strategy. You might have noticed that one scale, the one on the right, shows us the weight of one shape, the cylinder, in terms of the other two. We can apply this relationship to the scale on the left, all the while maintaining balance. Each of the two cylinders on the left can be replaced by one pyramid and two cubes. We say that we are substituting one pyramid and two cubes for one cylinder. What new information do we have? How is this helpful? The scale on the left now relates the weights of only two shapes, pyramids and cubes. We can reason that if 3 pyramids and 4 cubes balance 10 cubes, then 3 pyramids must balance 6 cubes. If 6 cubes balance 3 pyramids, then 2 cubes must balance 1 pyramid. Once more, we can substitute one shape for another, replacing one pyramid with 2 cubes. Notice that the scale on the right now expresses a relationship between cylinders and cubes without any pesky pyramids in the way. If one cylinder is equivalent to 4 cubes, then 3 cylinders must be equivalent to 12 cubes. It takes 12 cubes to balance 3 cylinders. In the next problem, we'll connect this algebraic thinking to algebraic notation. Tickets to a charity hockey game cost $12 for adults and $8 for children. A total of 150 tickets were sold for $1,640. How many of each type of ticket were sold? First, we can identify the unknown quantities. We don't know how many adult tickets or how many child tickets were sold. We'll choose the variables A and C to represent the number of adult and child tickets. Two linear equations can be written to model this situation. The first relates the number of tickets sold. A total of 150 tickets, some adult, some child, were sold. A plus C equals 150. The second equation relates the sales from these tickets. A total of $1,640 was made in ticket sales, some from adult tickets and some from child tickets. To determine the sales from the adult tickets, multiply the number of tickets A by the cost per ticket, 12. So, 12A represents the sales from adult tickets only. Similarly, 8C represents the sales made from selling child tickets. 12A plus 8C equals 1,640. Recall that in the scale puzzle, it was helpful to substitute one shape for another. Similarly, here we can replace one variable with an expression written in terms of the other. Solving equation 1 for C gives C equals 150 minus A. Next, we turn to equation 2. Where we once wrote C, we can now write 150 minus A, since these are equivalent. What has changed? How is this helpful? You might have noticed that we've created an equation in one variable, here A. We've reduced two equations in two variables to one equation in one variable. We can solve this linear equation by applying the distributive property, collecting like terms, subtracting 1,200, and dividing by 4. This gives A equals 110. We've figured out one of two unknowns. To find the second unknown, substitute 110 for A in either equation 1 or 2. I'll choose the first equation because the arithmetic is easier. C equals 40. In context, this means that 110 adult tickets and 40 child tickets were sold. This method of solving systems of linear equations is called solving by substitution. Before we explore a second algebraic method, let's take a quick look at how this method is connected to solving by graphing. Notice that if we were to graph the equation in one variable that we created through substitution, we'd see a vertical line passing through the point of intersection. An equation in the other variable makes a horizontal line. All lines pass through our solution. Next, we'll solve a different puzzle to develop a different algebraic method. Each row and column represents the cost of some combination of burgers, fries, and pops. What is the price of each item? Try to use reasoning. You might have made some comparisons between different pairs of rows and columns, like these two, or these, or these. There are many possibilities. I chose to compare the second row and third column. Notice that the two are similar. They have one burger and two fries in common. The difference is one burger shown here. So, this one burger accounts for the cost difference between the two combinations. Its price is $18 minus $12, or $6. The price of all burgers is then $6. Determining the value of one item is key to getting started. We are well on our way to unlocking the price of each menu item. For instance, the only unknown in each of the following highlighted rows and columns is the price of fries. Examining any of these reveals that an order of fries costs $3. We can determine the price of a pop in the same way. Each soft drink costs $2. We've used logic to determine the price of each menu item. Although we didn't express this strategy using variables, the thinking is nonetheless algebraic. Let's connect what might have been an intuitive strategy to symbolic notation. 2 t-shirts and 4 hoodies sell for $254. 4 t-shirts and 5 hoodies sell for $361. What is the price of each item? Each combination of tees and hoodies can be represented pictorially. In the previous menu item investigation, we were able to get started by comparing two different relationships and noticing that one quantity, for example the number of fries, was the same. How might you make one quantity, be it the number of tees or the number of hoodies, the same here? What new combinations can you create? If 2 t-shirts and 4 hoodies sell for $254, then by doubling, 4 t-shirts and 8 hoodies must sell for $508. In each relationship, above and below, there are now the same number of t-shirts, 4. Further, 8 contains 5, so the difference between the two total prices, $147, can be attributed to 3 extra hoodies. Dividing or sharing this amount between the 3 hoodies results in $49 per hoodie. Once more, determining the first unknown helps us figure out the second. How might we use variables and equations to show this strategy? Getting back to the beginning, the system can be modeled by the equations 2t plus 4h equals 254 and 4t plus 5h equals 361. T represents the price of t-shirts and H stands for the price of hoodies. Recall earlier that we doubled each quantity in the first equation. This creates an alternative for equation 1 in which the coefficient of t matches that in equation 2. Next, we compared the quantities in each equation and determined the difference. That is, we subtracted. We can also think of subtracting as adding the opposite. Because 4t minus 4t, or positive 4t plus negative 4t, is 0, the resulting equation, 3h equals 147, contains only one variable, h. We say that we have eliminated the variable t. This method is called solving by elimination. Dividing both sides of this equation by 3 gives h equals 49. To determine t, we can replace h with 49 in either equation 1 or 2. I chose the first equation. 4 times 49 is 196. Subtracting 196 from both sides of the equation gives 2t equals 58. Dividing by 2 results in t equals 29. In context, this means that the price of a hoodie is $49 and the price of a t-shirt is $29. A quick note. Some learners find it more efficient to create opposite terms at the beginning. For example, we might choose to multiply by -2 and add, rather than double and subtract. Let's analyze how this algebraic method connects to a graphical solution. The graphs of the two equations that we use to model the situation are shown here. If we were to add these two equations, we get 6t plus 9h equals 615. Notice that the graph of this equation also passes through the point of intersection. However, simply adding these two equations doesn't bring us any closer to a solution. It's correct, just not useful. Instead, we combined equation 1 and 2 in a more creative and promising way. By multiplying the first by -2 before adding, we generated an equation in one variable, 3h equals 147. This equation produces a horizontal line that, once more, passes through the point of intersection and, more importantly, shows us the value of one of the unknowns. Next, we'll apply our new understanding of solving systems algebraically. Which method, substitution or elimination, would you use to solve each system? Why? Take a moment to think about which would be more efficient. Each system can be solved by both substitution and elimination. Let's take a closer look at the system on the left. You might have noticed that, in the first equation, m is already expressed in terms of n. For this reason, I'll choose to use the substitution method. In the second equation, we'll substitute 1 plus 2n for m. 2 times 1 plus 2n is 2 plus 4n. 4n plus 5n is 9n. If 2 plus 9n is 20, then 9n must be 18. n equals 2. We can replace n with 2 in either equation. I'll choose the first. m is 1 plus 2 times 2, or 5. The solution to the system is m equals 5 and n equals 2. We can express a solution to a system of equations as an ordered pair. Let's wind it back and analyze the second system. It is possible to solve this system using substitution, but it's not advisable. Because solving for p or q in either equation means introducing several fractions to the mix, I'll choose to use the elimination method. To eliminate one variable, its coefficients must be opposites. Multiplying the first equation by 2 creates an equation in which the coefficient of p is 10. And multiplying the second equation by -5 creates an equation in which the coefficient of p is -10. We have the opposites we're looking for. Adding these two equations eliminates p, leaving an equation in q. q equals -3. We can replace q with -3 in either equation. 3 times -3 is -9. -9 plus 19 is +10. Since 5p plus 10 is 0, p is -2. The solution to the system is p equals -2 and q equals -3. One last application. A scientist needs to make 200 milliliters of a 42% alcohol solution. She mixes 30% alcohol and 50% alcohol solutions. How much of each solution is needed? It will be helpful to organize this information in a table. The scientist has two solutions available to her, a weaker 30% solution and a stronger 50% alcohol solution. We also have some information about the solution formed by mixing the two. First, we'll think about the volume of each of these solutions. Let X be the volume of the weak solution and Y be the volume of the strong solution. The scientist needs 200 milliliters of the mixture. We also need to think about the volume of alcohol within each of these solutions. 30% of the volume of the weak solution is 0.30 times X. 50% of the volume of the strong solution is 0.50 times Y. 42% of the mixture's 200 milliliters is alcohol. 0.42 times 200 milliliters is 84 milliliters. Adding the two parts to form the whole gives us the two equations that model this scenario. This system could be solved by graphing, by substitution, or by elimination. I'll choose to apply the elimination method. Multiplying the first equation by -0.50 generates a y term opposite to that in the second equation. Adding these two equations gives an equation in one variable. -0.20x equals -16. Dividing each side of this equation by -0.20 results in x equals 80. 80 can be substituted for x in either equation. I'll choose the first. The arithmetic is much easier. Y equals 120. This means that the scientist needs 80 milliliters of a 30% alcohol solution and 120 milliliters of a 50% alcohol solution. Let's return to the table and check these results. 80 milliliters of the weak solution and 120 milliliters of the strong solution do make a total of 200 milliliters of the needed solution. 30% of 80 milliliters is 24 milliliters. 24 of the 80 milliliters of this solution is alcohol. 60 of the 80 milliliters of the second, stronger solution is alcohol. We can determine the total volume of alcohol in the mixture by adding these two values. 24 plus 60 is 84, our earlier calculation of 42% of 200. Intuitively, this makes sense. Mixing some volume of a 30% solution with some volume of a 50% solution will result in a mixture in which the percent falls somewhere between the two. Because 42% is closer to 50% than 30%, it also makes sense that the scientists needed more of the stronger solution than the weaker solution. Next, we'll connect what and how we learned to your child's mathematics curriculum. This video addresses several learning standards in the Foundations of Math and Pre-Calculus 10 curriculum. In content, we learned about systems of linear equations. The curricular competencies describe what it means to do the math. Let's highlight a couple that were elicited in this video. Beginning when we solved the shape and menu item puzzles, we developed an understanding of two algebraic methods for solving systems of equations. Later, we applied this understanding to model with mathematics in situational contexts, for example, the chemistry scenario. Throughout, we were encouraged to think creatively and be both curious and persistent problem solvers. We hope that you enjoyed this video and found it helpful when supporting your child in their mathematics learning. Please check out the other videos in this series. Thanks for watching.